Okay, the last hurrah, page 11 in your packet. We're going to start with some derivatives of inverse trig functions. This will be a good test of your memory to see what you remember. If you recall, I used to look at what comes after the inverse trig function, and we would say that's u. And then I would say, okay, if u is 2x, then u squared is 4x squared. And then du, which is the derivative of u, is 2. I would then take all of that information, y prime, because we're doing the derivative of inverse sine, it's this formula, 1 over radical 1 minus u squared, which is 4x squared, times du, which in this case is 2. So let's see, how well do you remember that? Good? Okay, second one. In this case, again, u is radical x, u squared, if I square that, I'm going to get plain old x, and then the derivative of radical x is 1 over 2 radical x. So that's what I have for my setup. The derivative formula, if you recall, 1 over 1 plus u squared, which is x, times the derivative of u, 1 over 2 radical x. Obviously, I can simplify that, but I don't care right now. It's good enough. And then finally, I have inverse secant. And if I look at this example, u is x squared. U squared would then be x to the 4th, and du would be 2x. That's my prep work. So when I take my derivative, the formula for inverse secant, 1 over u, which is x squared, square root of u squared minus 1 times du. Okay, so now here's the fun stuff, because as you know, we're doing antiderivatives. Those are derivatives. So what we have to do now is we are going to take these answers and figure out, okay, how do I go backwards and get the original equation? If this is what I'm starting with, how do I go backwards and get this? Well, no tricks here. It's formulas. You have to recognize them. Oops, hold on, let's see here. Okay, so what I'm looking at here, if I notice I have an integral that kind of fits this format, 1 over radical a squared minus u squared du, then I know my answer is inverse sine u over a plus c. In this case, what you're looking for, when you have the square root of a constant squared minus a variable squared, you want to be thinking inverse sine. Okay? Again, we're just taking the derivatives we did before and kind of going backwards. The other example that you have, if you have a constant squared plus a variable squared, no radical sign, then inverse tan. And then finally, when you have this, I always look at this, when the u's are together like that, you have something in front of the radical and then a variable squared under the radical. That's the clue that it's secant inverse, okay? These are very rare problems. It might show up on the multiple choice section of the AP test. As we go through the review exams, you'll notice it doesn't show up a lot, but we got to be ready for it if it does. If I look at these first two examples, what I notice is that they look practically identical. The only difference between these two examples is an x on top of the first fraction versus a 1 on top in the second fraction. Your instinct when you integrate should always be a u substitution. So I'm going to do this first problem, and I'm going to say, okay, let u equal 4 plus x squared. When I take the derivative, du will then be 2x dx. This is what you want to look for. Notice that in this case, I have the x dx right there. And the 2 I can take care of by putting a 1/2 out in front. So I can say 1/2 the integral du over u, and then I just get my answer, 1/2 ln absolute value of u, which is 4 plus x squared, plus c. So that's a nice simple one because it's a u substitution. Let's focus on this next problem. If I tried to set up the same u substitution that I did in the previous one, I wouldn't have that extra x dx, so I can't do it. So this is where I think, okay, does this match any of my formulas? And actually, it's kind of looking like it matches inverse tan. For, it looks like I have a constant squared plus a variable squared. This is going to be all about inverse tan. So what I want to do here, I always kind of set this up. What constant is getting squared to get 4? 2. Okay, what variable is getting squared to get x? X. And now I look at this and say, okay, if u is x, because that's the variable that's getting squared here, then du will be dx. So when I rewrite this integral, it's the integral of 1 over a squared, because a is 2 and 2 squared is 4, plus u squared, because u is x and this is x squared, du. And that fits my inverse tan formula exactly. If you follow along with the inverse tan formula, my answer will be 1 over a, which is 2, inverse tan u over a, which will be x over 2 plus c. And that's your answer for this question. Let's try the next one and see what happens. If I look at this one, I've got what looks like a constant squared minus a variable squared. It's looking like inverse sine. So that's kind of my thinking. I think that's what I have. In this case, I'm going to let a equal 4 because that's the constant that's getting squared to get me the 16. Let u equal x, that's the variable that's squared. And then du will be dx. When I rewrite this whole thing, I've got du over the square root of a squared minus u squared. Now, whether or not that du is sitting on top or on the side, it doesn't matter. It's the same thing. So now, following my inverse sine formula, my answer is inverse sine u over a, x over 4 plus c. There you go. Final answer. What do you think? Not too bad? Okay, flip the page. Let's see what we got going on. You're going to see a couple little tricks in here, but they're really not too bad. Hopefully you're understanding these. If I look at the first equation on the top of the next page, I have 1 plus 16x squared. So it looks a little different. It has the plus sign. It makes me think tangent. I'm going to say a is 1. That's the constant that's getting squared. U is 4x because that's what's getting squared to get me the 16x squared. Therefore, du will be 4 dx. So this is where we got to watch out. Do I have that 4 in here? No. So I rewrite it as 1/4 the integral du over a squared plus u squared. That's my inverse tan formula. Final answer, 1/4 times. For inverse tan, what I have is 1 over a, so 1 over 1, inverse tan, u over a, so that's 4x over 1, plus c. Now, of course, I don't need all these 1 over 1s and 4x over 1s. I'm just trying to reiterate the point to you, okay? Looking at this next one, little tricky. If I look, does it fit the format? Do I have a variable, or I'm sorry, a constant squared plus a variable squared? Yes. In this case, a is 1. U, what variable is getting squared to get me e to the 2x? E to the x, okay? And then what's du gonna equal? Well, du is the derivative of this. So it's e to the x dx. And again, look at what's happening here. I need e to the x dx for du, and that's exactly what I have sitting on top of my fraction. So when I set this up, when I rewrite this, I've got the integral of, all of that is up there, du over a squared plus u squared. Therefore, my answer is 1 over a inverse tan u over a plus c. Final answer, okay? Now, if you look at the next example, it's almost identical, okay? We just did a problem where the denominator is 1 plus e to the 2x, and now I'm doing a problem where the denominator is 1 plus e to the x. Well, guess what? If you look at this and just do a u substitution, let u equal 1 plus e to the x, and then du is e to the x dx. When I rewrite this, it's the integral of du over u. And then what's my answer for that? Well, we all know that the integral of du over u, ln absolute value 1 plus e to the x plus c. That's all you have to do there. You want to get in the habit of your first instinct when you have an integral is you're going to try a u sub. If it works, wonderful, you're on your way. If it doesn't, that's when you want to start thinking, maybe it's one of those inverse trig formulas, okay? If I look at the next example here, I've got x dx over 4 plus x squared. Following along here, can I do a u sub? If I do a u sub, what will u equal? Well, if I let u equal 4 plus x squared, does it work? Well, du would be 2x dx. This is the trick. Do you have the x dx that you need? Yes, perfect, u sub. 1/2 integral du over u. Final answer, 1/2 ln absolute value 4 plus x squared plus c. Love it. Okay, 2 more examples. Looking at these, it's a little different. Almost identical. One has an x on top, one doesn't. So I'm guessing one's going to be a u sub and one's going to be a trig, an inverse trig problem. Because this problem, the last one on the page, on page 12, has the x on top, there's your u sub. 9 minus x squared for u, du is negative 2x dx. So I have to put a negative 1/2 out in front, integrate, and then I've got the x dx, so that's du over, and when I look at this, it's the square root of u, okay? So this is not an ln problem, guys. This is u to the negative 1/2. So this becomes negative 1/2, that's right there, times. I have to add 1 to my exponent, so that's going to give me a u to the 1/2, and I divide by my new exponent, so I'm dividing by 1/2, which is the same thing as multiplying by 2, plus c. Final answer, negative, let's see, radical 9 minus x squared plus c. That's your final answer there. That's nice. I like that. When I go to the other example on the left-hand side of the page, I don't have that extra x on top. That forces me to do an inverse trig. A is 3. That's the constant that's getting squared. U is x. That's the variable that's getting squared. Du is the derivative of x, 1 dx. So when I set up my integral, I've got du over radical a squared minus u squared, piece of cake. That sign, my final answer is inverse sine, and for inverse sine, I've got u over a plus c, and we are done.